Today, we are doing exactly what we promised. We're moving past the sort of abstract hype of AI
Right.
and diving right into the engineering
And your
fundamentals.
hands dirty.
Exactly. We are tackling the core mechanics of how modern machine learning systems actually learn, how they test themselves, and maybe most importantly, prove they can make reliable decisions out there in the real world.
hmm
It's really time to open up the ML toolkit.
Yeah, and our source material for this deep dive is, it's really focused on the definitions that truly matter. The definition of the learning problem itself, how we manage the data, which is critical,
Yeah.
and the metrics we use for evaluation.
Right.
Our mission really is to break down these fundamental concepts, focusing on that single, crucial engineering goal, achieving generalization.
Generalization, that's the key word, isn't it? The ability for the system to perform well on data it has never, ever encountered before. But, okay, before we even get there, we need the blueprint, right? Machine learning, at its heart, it's defined by three elements. You're improving some measure of performance, P.
KDP.
When performing a certain task, T.
Task T.
Through some training experience, E.
That TPE framework,
Yeah.
it's absolutely foundational. If we use that classic example from the sources, the drafts or checkers learning problem, you can see how simple the concept is, even if the execution gets complex. The task, T, is playing the game of drafts.
Split up.
The performance measure, P, is easily quantified. It's the percent of games won against opponents.
Okay.
And the training experience, E, well, that's the machine playing practice games against itself over and over.
Oh, okay.
That definition, T, P, E, it pretty much dictates every single engineering choice that follows.
And most of the practical tasks that fit into that blueprint, they lead us straight to the two major categories that determine the entire architecture of our model.
Yep.
Let's talk about that primary split, classification versus regression.
Right. And the primary differentiator here is really simple. It's the type of output the model is expected to produce. Is the answer a label or is it a number? That's the core question.
So if the model is sorting inputs into specific predefined buckets, could be 2 buckets, could be 200, then we're talking classification.
Exactly. Classification means the task is to identify which of a set of categories a new observation belongs to. The target variable is inherently categorical.
Okay.
Think about classifying songs by emotion, happy, sad, angry, or identifying objects in a picture as human or not human.
Or the classic email example, spam or not spam.
Yeah, that's a perfect binary example. And the distinction between binary and multi-class classification is just that. The number of available labels. Spam detection is binary, yes, no.
But like classifying the 3 species of the iris Stetosatosa versicolor virginica, that's multi-class.
Precisely. Now contrast that sharply with regression. The objective of regression is totally different. It's to predict continuous output values.
So numbers, not labels.
Exactly. The target variable here is continuous, meaning it can take, theoretically, any value within a given range. For example, predicting the software development effort required for a project in, say, person months.
Or predicting tomorrow's temperature.
Perfect example. It's a numeric prediction, not a label assignment. Although it's worth noting, the sources do mention that sometimes regression is loosely regarded as numeric classification, but the distinction is generally quite clear.
Okay, so let's say you have a massive multi-class classification problem. Like the sources mentioned, classifying handwritten digits 0 through 9. That's 10 classes. You don't necessarily need one giant algorithm to handle all 10 decisions at once, right?
No, absolutely not. You can break that big task down using simpler binary classifiers. This is where some clever engineering comes in.
Okay.
We use 2 main strategies here. The first, and maybe simpler conceptually, is one versus all, sometimes called one versus rest.
One versus all. How does that work?
You train a dedicated binary classifier for each class. So for the 10 digits, you train 10 separate detectors, a 0 detector, a 1 detector, a 2 detector, and so on.
Ah, I see.
When you need to classify a new image, you run it through all 10 detectors, and you basically pick the class whose classifier outputs the highest confidence score. I'm most confident this is a 7.
That feels pretty efficient, actually. But the second strategy, one versus one, that sounds like it could get computationally heavy up front.
Oh, it absolutely can. In one versus one, you train a binary classifier for every single pair of classes. You're only ever asking a classifier to distinguish between 2 specific classes at a time.
Every pair. So like a 0 versus 1 classifier, 0 versus 2, 0 versus 3, all the way up to an 8 versus 9 classifier.
Exactly. If you have nil classes, you need to train Muller choose $2 2 classifiers. For 10 classes, that's $10 times 922, which is 45 separate models.
Wow, 45 models just for digits.
Yep. You have to train them, store them, manage them. Now, it can sometimes lead to very high accuracy because each classifier has a very focused job, but the engineering cost training time storage is substantial. That's a major design consideration you have to weigh.
Okay, that makes sense. But whether we're building this complex one versus one system or just a simple linear regression, the whole thing kind of falls apart if the model can't perform reliably when it sees inputs it has never encountered before.
You've hit the nail on the head.
This demands really strict data separation, right? And this is where clarity is absolutely essential.
This is possibly the most critical section for anyone wanting to do ML engineering seriously. We absolutely need 3 distinct roles for our data, each with a unique purpose that must not be mixed up.
All right, lay them out for us. The first one's obvious, I think. The training data set.
Yep. That's the data used for the actual learning process itself to fit the internal parameters of the model. Think of things like the weights and biases inside a neural network. That's what gets adjusted during training.
Okay, parameters learned during training. What's next?
And then we get to the slightly trickier one, the validation data set. This is often confused with the test set, but it serves a fundamentally different crucial purpose.
How so?
The validation set is used to tune the hyperparameters. These aren't the parameters learned by the model, but the structural choices made by the engineer. Things like the number of layers in your network, the learning rate, the type of activation function you use.
Wait, hang on. So the validation set isn't about training the model's guts. It's about training the trainer.
Huh?
Or checking the architect's blueprint. Why the separation between parameters and hyperparameters?
That's actually a great way to put it. Parameters are learned by the algorithm internally, defining the function. Hyperparameters are external settings you, the engineer, choose that control how the algorithm learns. You need the validation set to get feedback on your choices. The hyperparameters. Are they good choices? You test different architectures or settings on the validation set and see which performs best. If you tested these choices on the training data itself, you just end up picking the architecture that best memorized the training data, noise and all.
Okay, that makes perfect sense. You need an independent referee for your own design choices.
Mm.
And that leaves the third one, the test data set.
The test set. This one must be kept completely pristine, locked away, totally independent. Use it only once, right at the very, very end.
Only once.
Only once. To provide the final, unbiased evaluation of your chosen model's performance on truly unseen, realistic data. If you make the mistake of tuning your model, even just the hyperparameters using the test set, you've essentially cheated. You've leaked information about the flubble exam, and your reported performance score is basically worthless. It won't reflect real-world performance.
Wow, okay, so training learns parameters, validation tunes hyperparameters are choices, and testing gives the final grade. Got it.
And this whole meticulous separation, this careful process, it's all in pursuit of generalization.
That magic ability to map input to output correctly, even when the input is a bit different from the training example.
Exactly. And when generalization fails, well, that's when we face the 2 great enemies of machine learning.
Ah, yes. Underfitting.
Mm.
And overfitting.
Underfitting is when your model is just too simple. It hasn't captured the underlying pattern in the data. It's incapable of getting a low enough error rate even on the training set itself. It just doesn't learn well enough.
Okay, too simple. And overfitting.
Overfitting is the opposite problem and often more insidious. This is when the model is too complex for the amount of data it has. It starts learning the noise in the training data, not just the signal.
So it fits the training data perfectly.
It looks amazing on the training set, but then the gap between its excellent training error and its terrible testing error is massive.
Right. I've heard that classic kind of funny example of the neural network that learned to classify wolves. But it turned out it was actually just classifying snow because all the wolf pictures happened to be taken against snowy backgrounds.
That's pure overfitting. A perfect textbook example. The model memorized a spurious correlation in the background instead of learning the actual features of the wolf.
Exactly. So how do we formally estimate how prone our model might be to this kind of failure?
Well, beyond just using the validation set, when training data is particularly limited, we often turn to cross-validation, or CV procedures.
Okay, cross-validation. I've heard of K-fold cross-validation. That's the standard.
That's the workhorse, yes.
Yeah.
Instead of just having one static, maybe small validation set, you divide your available training data into K distinct equal-sized subsets, or folds.
K-folds.
Then what? Then you train K separate times. In each run, you use K1 of those folds combined as your training data, and you test the resulting model on the single fold that was left out.
Ah, so each fold gets a turn at being the test set for that run.
Precisely. And crucially, the final performance estimate isn't from just one run. It's the average performance across all K runs. This gives you a much more robust estimate of how well your model is likely to generalize. A common choice for K, something reasonable, is often around Dillinger approx $10.
So the big advantage is you get to use almost all your data for training in each run, just holding out a small piece. But the downside seems obvious. You have to train the entire model K times.
That's the trade-off. More computation time.
Which brings us to a really crucial engineering decision, doesn't it? The choice of K itself. It's not arbitrary.
Not at all. The choice of dollars is a classic trade-off between essentially accuracy of the estimate and the resources you have, time and computation.
How does that play out?
Well, if you choose a large number of folds, say K, $5 a one, or even the extreme case called leave one out CV, where K equals the number of data points,
Whoa.
you get a very small bias. Your estimate of the true error rate is likely to be highly accurate, very close to the real value.
Sounds good. What's the catch?
The catch is twofold. First, the computational cost goes way up. You're training many, many times. Second, you actually increase the variance of the estimate. The performance score might bounce around more unpredictably between the different folds.
Okay, so large K, accurate estimate, but slow and potentially jumpy results. What about small k?
Small k, say K3 or K5, obviously reduces computation time significantly. It also tends to reduce the variance. The estimate is more stable. But
There's always a but.
there's always a but. It results in a larger bias. Specifically, your estimate of the error rate will tend to be conservative. It will likely be higher than the true error rate your model would achieve if trained on all data.
Conservative, meaning it makes your model look worse than it might actually be.
Exactly. So think about it. If you were a developer working on, say, a small embedded device with limited power and time, or maybe your results are needed instantly for a massive online service.
Right, speed is critical.
The pressure to choose a small dollar would be immense. You'd sacrifice the accuracy of your estimate for speed and stability. You'd be essentially betting on speed, knowing your evaluation probably underestimates your model's true capability. That's a key engineering risk assessment right there.
Fascinating trade-off. Okay, so beyond just estimating generalization with things like cross-validation, we need methods for actively improving it. You mentioned simple things like stopping training at the right point, but what's the more sophisticated approach?
Well, probably the most important technique here is regularization.
Regularization.
It's basically any modification you make to the learning process that's specifically intended to reduce the generalization error, possibly even at the cost of slightly increasing the training error.
Wait, you want to make the training error worse? How does that help?
It sounds counterintuitive, right? But think of it like this. Overfitting happens when the model becomes too complex, fitting the noise. Regularization works by adding a penalty term to the error function itself, a penalty based on the complexity of the model.
A complexity tax.
That's a perfect analogy. It's a tax on complexity. It discourages the model from learning overly complex, jagged functions that fit every single training point perfectly. If the model tries to do that, the regularization term kicks in and increases the overall error score it's trying to minimize. This forces the model to find a simpler, smoother mapping that hopefully captures the underlying trend rather than the noise.
Okay, so it enforces simplicity to avoid memorizing noise. That makes sense.
Exactly. It's a core technique for fighting overfitting.
All right, so we know how to structure the data, estimate generalization, and even improve it. Now we need to actually quantify performance. We need metrics. For classification tasks, you said everything really starts with that foundational visualization tool, the confusion matrix.
The confusion matrix is absolutely essential because just saying a model is 80% accurate can hide a multitude of sins. The matrix moves beyond just right or wrong and shows you how the model is getting things right and, more importantly, how it's getting things wrong.
So what does it look like?
It's basically a taber, a contingency table or error matrix. Typically, the columns represent the classes the model predicted, and the rows represent the actual true classes.
Okay, predicted versus actual.
And the cells in the table then count how many instances fall into each combination. This gives us the four fundamental numbers that drive almost all classification metrics.
The famous four: true positive, TP, false positive, FP, true negative, TN, and false negative, FN.
Those are the ones: true positive, correctly predicted positive, true negative, correctly predicted negative, false positive, incorrectly predicted positive, and false negative, incorrectly predicted negative.
a miss.
Once we have those counts from the matrix, we can calculate the actual metrics. The most basic one is accuracy, right?
Yes, accuracy is just the total number of correct predictions, TP plus TN, divided by the total number of predictions. Simple. Its inverse, the error rate, is just the incorrect predictions divided by the total, or simply 1 minus accuracy. But you hinted earlier that accuracy can be dangerous. Let's use that running example you mentioned. Trying to predict rare financial fraud, maybe it only happens in, say, 1% of transactions.
Okay, highly imbalanced data.
If our model is lazy and just predicts no fraud for every single transaction, what's its accuracy?
Well, it gets 99% of the cases right, the non-fraudulent ones. So it achieves 99% accuracy.
Wow, 99% accurate, but completely useless because it never catches any fraud.
Exactly. Accuracy completely fails us here because the data is so imbalanced. It gives a misleadingly rosy picture. That's precisely why we need to rely on precision and recall to tell the real story.
Okay, let's break those down. Precision first. The formula is true positives divided by the sum of true positives and false positives, TP plus FP. What does that actually tell us about our fraud model?
Precision measures the quality of your positive predictions. The memorable phrase the sources sometimes use is, precision equals 1 means nothing but the truth.
Nothing but the truth.
It answers the question, of all the transactions that the model flagged as fraud, predicted positives, TP plus FP, how many actually were fraud? If your precision is low, it means your model is generating a lot of false alarms. FP, you're wasting investigators' time chasing ghosts.
Okay, so precision is about avoiding false alarms. Now, recall, which is also called the true positive rate or sensitivity. The formula is true positives divided by the sum of true positives and false negatives, TP plus FN. What quantity does this measure?
Recall measures the quantity or completeness of your positive predictions. Its memorable phrase is, recall equals 1 means the whole truth.
The whole truth.
But answers the question, of all the real fraudulent cases that actually existed in the data, actual positives, TP plus FN, how many did the model successfully catch? TP. If your recall is low, it means real fraud, FN, is slipping through your system undetected. That could be catastrophic.
So in the fraud example, you probably care a lot more about recall than precision, right? Better to have a few false alarms than to miss actual fraud.
Very likely, yes. High precision minimizes false alarms, saving resources. High recall minimizes missed cases, reducing risk. You often have to decide which type of error is more costly based on your specific task, your TPE goal.
And is there a metric if you need to balance both? You can't always prioritize one over the other.
Absolutely. That's where the F1 score comes in. It's the harmonic mean of precision and recall, giving you a single number that balances both. It's useful when you need both good precision and good recall. And for even more nuanced analysis, especially when looking at trade-offs at different decision thresholds, we use tools like the ROC curve, which plots recall, true positive rate, against the false positive rate.
Okay, lots of ways to measure performance beyond simple accuracy. Now, to try and ground all this theory with a specific type of model, let's briefly look at one architecture mentioned in the sources. Decision trees.
Decision trees. They're a really fundamental model type and a great one to discuss because they're so interpretable.
Interpretable, meaning you can easily understand why they make a particular prediction.
Exactly. Unlike, say, a complex neural network which can feel like a black box, a decision tree lays out its logic very clearly. They're also great because they can handle different types of variables, easily categorical, numerical, and they're pretty robust to missing values in the data. Plus, they're relatively easy to update if new data comes along.
So what's their structure like? I picture a flowchart.
That's basically it. You have a root node at the top, which represents the entire data set. Then you have internal nodes, which represent tests on specific features or attributes. And these nodes split into branches leading to other nodes, eventually ending up at leaf nodes, which represent the final decision or prediction.
How do they actually perform classification or regression using this structure?
They work by systematically dividing the feature space, all the possible input combinations, into several, usually rectangular regions. If it's a classification tree, every data sample that ends up in a particular final leaf region is assigned the class label that is most common, the majority vote, among the training samples that ended up in that same leaf.
Okay, majority vote in the leaf. And for regression?
For a regression tree, it's even simpler. The prediction for any sample landing in a specific leaf region is just the average value of the target variable for all the training samples that fell into that leaf.
Makes sense, but given how they keep splitting the data into smaller and smaller regions, I can see how they'd be really susceptible to that overfitting problem we talked about earlier.
Oh, they absolutely are. Highly susceptible. If you let the tree grow without any limits, it will keep splitting until every leaf is pure or contains only a single data point from the training set. It perfectly memorizes the training data, including the noise.
So it won't generalize at all.
Right. That's why a crucial part of using decision trees is the grow then prune strategy, often associated with algorithms like CART, classification, and regression trees.
Grow then prune.
Yeah. The idea is, first, you intentionally grow a very large, overly complex tree that definitely overfits the training data. Then you systematically prune it back. You remove branches or nodes according to certain criteria, often involving a penalty for the complexity or size of the tree, kind of like regularization, aiming to find the smaller subtree that generalizes best, usually tested on a validation set. The goal is a tree that's large enough to capture the signal, but small enough not to fit the noise.
Right. Finding that sweet spot between underfitting and overfitting again.
Always the balance.
This deep dive has really shown, I think, that machine learning isn't magic. It's a series of very precise engineering choices. And maybe the most essential takeaway here is knowing how to differentiate between classification models, where your output is a category or label, and regression models, where your output is a continuous number.
Absolutely. Critical distinction.
Getting that right, combined with how meticulously you separate your training, validation, and test data, and how carefully you choose your performance metrics based on what actually matters for your goal, that seems critical for achieving reliable results, whether you're, maximizing the recall of a fraud detection system or maybe minimizing the false alarms from a medical diagnostic tool.
Precisely. And, if we connect this knowledge back to the practical reality of deploying these systems, think again about that trade-off in k-fold cross-validation we discussed.
Okay.
We established that a higher dollar gives you a more accurate estimate of the error rate, low bias, but it costs a lot more computationally and can have higher variance. Now, imagine you were deploying a system where computation was severely limited. Maybe it's running on a tiny embedded chip, or it's a web service needing super low latency for millions of users.
You'd be forced towards a small k.
You'd be absolutely forced to choose a small dollars, like 3 or 5, just to make it feasible. But remember, small k introduces that large bias. Your estimate of the system's error rate will be conservatively high. It'll probably look worse than it really is.
Right.
So, here's the provocative thought to maybe leave you with. How would the pressure of that real-world resource constraint fundamentally change your decision-making? How would it force you to adjust your confidence threshold when finally deciding whether to accept that model for deployment? You'd essentially have to accept launching a model knowing that your own evaluation metrics are likely pessimistic, simply because the practicalities of your situation dictated a computationally cheap and therefore biased way of testing it. It highlights that constant tension between theoretical correctness and practical constraints.
That's a fantastic point. Balancing the ideal with the achievable, knowledge understood and hopefully knowledge applied.